Welcome to the pilot brief, guys. So I'm starting a new series of aviation meteorology today. Our first chapter is atmosphere. So what is atmosphere? The atmosphere is envelope of gases that surrounds the earth. It's held by the gravity. So think of that. Why we study atmosphere as a pilot? Because atmospheric weather, flight safety and performance. Why we study weather? It's basically all in weather. We have clouds, turbulence, icing, and we have to fly through it, or we have to just bypass through it. So we should know what is coming in for front of us. Flight safety, handling, and visibility structure. Like when we are going to land on the runway, we should know what kind of visibility would be there, and what will be the possibilities to land there, winds condition, and all. It also affects the performance of the aircraft, like air density, temperature, and pressure determine the takeoff and landing, climb rate, engine output. So it's important for every pilot to study about atmosphere. So it's our first chapter in MET. That is basic thing. So let's start with the composition. So our atmosphere consists of various constituents: nitrogen, oxygen, carbon dioxide, and other gases. Nitrogen is 78% by volume, oxygen is 21%, and carbon dioxide is 0.03%. Remember this, it's asked most of the times in DGCA exams. Another gas is 1%. And most important part of atmosphere is water vapor. And one more question occurs in exam, that percentage of composition by weight. So it's 3:1. You can remember weight is like this, so if you tilt it, it will become 3. By volume, it's 4:1. So we can say like that, percentage of composition by weight of nitrogen to oxygen is 3:1, and percentage of composition by volume of nitrogen to oxygen is 4:1. As I told you, water vapor is the most constituent part of our atmosphere. So if we think why, so why is here? Water vapor drives cloud formation, precipitation, icing, fog, and thunderstorm even. So it directly influences all the weather conditions that occurs. So that's why it's the most constituent part of our atmosphere. So here we read, air is never completely dry. It's range from 0 to 4%, depends on temperature, location. Warm and humid air holds more vapor than cold and dry air. So as temperature is more, so water vapor will be more. Temperature is less, water vapor will be less. Now we come to temperature layer, most basic concept of learning about atmosphere. So first layer is normal layer. It's normal layer, it's within earth, it's within earth, and tropopause. Here, as we climb or as we gain altitude, temperature decreases. For example, if we go to a mountain, temperature decreases. As we gain height, temperature decreases. Second layer is isothermal layer. From the name itself, we can say iso means when things ceases, means remains almost constant. Here also written temperature stays constant. Commonly it's in tropopause boundary. Tropopause is the layer between troposphere and stratosphere. Then comes to inversion layer. Inversion layer is above troposphere basically. In inversion layer, temperature rise with altitude. Like as we climb more or gain more altitude, temperature also rises. It's due to ultraviolet rays basically, and ozone layer. Here ozone traps the heat. So here we comes to our layers of the atmosphere. So for basics, we have three layers in the atmosphere. First is tropopause, second is stratosphere, third is mesosphere. This is the boundary layer. It's not a layer, but it's boundary between tropopause and stratopause. Here we also have a stratopause. It's also a boundary layer. So what is tropopause? Tropopause, all the weather condition, all commercial flights operate here. It's range from 0 to 11 kilometers, or we say 0 to 36,000 feet. Here, our lapse 8 is 1.98 degrees Celsius per 1000 feet, or we can say 6.5 Celsius per kilometer. Tropopause, it's a boundary between stratosphere and troposphere. Temperature ceases to fall. It means temperature stop decreasing. Jet streams also form here. So it's a normal layer, and this tropopause is isothermal layer. Iso, remember, remains constant. Then comes to stratosphere. It's above tropopause. It's from 11 to 50 kilometer. Stable, dry, high altitude jet streams. Mostly military aircraft operate here. Then comes the last layer of the atmosphere. It's above everything, above commercial flight levels, relevant for re-entry and satellites. Mostly seen by mostly satellites operate there. Rockets pass from this layer, and our radar waves reflects from this layer. So let's get deep into this topic. So first is troposphere. So troposphere, this is the layer of the Earth atmosphere where temperature decrease. Here temperature decrease as altitude increase. It's the lowest and the dense layer in the atmosphere. Its altitude range from 0 to 11 kilometers and 36,000 feet. It's vary with the mid latitude, temperature, season, equator, poles. It's different everywhere. Like if I say on in equator, it's 16 kilometers, Basically, we can say around 55,000 feet. And on poles, it's 8 kilometers. Remember this? It's home for weather. All weather phenomena, clouds, rain, snow, turbulence, storm, everything occurs in this layer. So we called it as unstable layer. Here is the lapse rate. Remember this, it comes everywhere. Decreasing temperature with increase in height or altitude. So average lapse rate is 6.5 degrees Celsius per 1000 meter, means 6.5 degrees Celsius per kilometer, and 1.98 degrees Celsius per 1000 feet. For calculation, we use this to round off. This layer consists of 3/4 of the total atmosphere weight, like 75% to 80% of total atmosphere mass, and approximately all of atmospheric water vapor. So let's dive into the another topic, tropopause. It's the crucial boundary. It's the boundary between troposphere and stratosphere. It's a non-uniform layer, means due to latitude, season, temperature, and time, it shifts its height. Like it's a first of all, it's a isothermal zone. Within the tropopause, the temperature ceases to fall with increase in altitude. Means temperature almost remain same as it was at 36,000 feet or 11 kilometers. It's not always at the fixed ceiling, it's a dynamic altitude. Its height varies with, I told you, the temperature, latitude, season, time of the day. It's higher and colder near the equator, lower and warmer at the poles. Now you will be thinking, like, equator is hot, so why tropopause is cold? Because at equator, tropopause height is 16 kilometers, and at poles, it's half 8 kilometers. So, as I told you, as the height increase, temperature decrease. It's a normal layer. So now I will explain why things that varies the tropopause height. First is latitude. Polar height is lower. Season. Winter are low. Temperature cold is low. Time, like if it's noon, then it's hot, so more. night, cold, less. Average height we consider is at 36,000 feet. One more thing to tell you. Tropo means turning. Let's go to stratosphere, right? Yeah, one more thing I have to tell you, that all the significant things happen in at the height of tropopause. It's the maximum height for cloud top. There is a presence of jet stream, cat, clear air turbulence is present there. Max wind speed, it's always around tropopause. So let's start with stratosphere. It's the stable layer. It extends from troposphere to 50 kilometers. Means it's from troposphere and up to 50 kilometers. Here temperature inversion occurs. Means temperature increase with altitude increase. Temperature increase as altitude increase. Tropopause then up to 50 kilometers. Altitude extends from tropopause to 50 kilometers. It contains the ozone layer, which is 20 to 30 kilometers. Basically, we consider it as 25 kilometers, which absorbs the ultraviolet rays. That's why temperature increase here. It's a stable and dry layer with low humidity, minimum weather condition. It's a stable layer. This is important. In this layer, nacreous clouds are formed, which is also called as mother of pearl clouds. It's formed between 20 to 30 kilometers in winter. Winter in polar region. See, it's stable as I said, so no weather occur here. Let's go to another. Our last layer is mesosphere and thermosphere. So let's start with mesosphere. Mesosphere range from 80 to 50 to 85 kilometers. It extends from 80 to 85 kilometer. It's important. Here the temperature decrease sharply with altitude. Again, it got a normal layer. And here we found noctilucent cloud at that height. And it's observed as glowing at twin light, means during sunrise or sunset. Let's go to thermosphere. It is also called as exosphere. Above 85 kilometers. Here temperature increase with height, again due to ultraviolet rays, and it's crucial for radio wave propagation. Here auroras also occur. Auroras like in north and south pole we get a greenish and blue type of phenomena. That's called aurora. Now let's go to International Standard Atmosphere. It's just called ISA. ISA is a theoretical model of the atmosphere used as a reference for the aircraft performance, instrument calibration, and planning. So we can say it's basically a constant or a standard set for all the aircrafts flying, so they can be calibrated from same reference. So why ISA is needed? For calibration first of all, then to design and test aircraft. So there are few things to remember for ISA. At MSL means sea level temperature, called MSL, mean sea level temperature. Is 15 degrees Celsius. Sea level pressure at MSL is 1013.25 hectopascal and 29.92 inches of mercury. 29.92 inches of mercury. Lapse rate is minus 6.5 per thousand meter, or we can say minus 6.6 decimal minus 6.5 degrees Celsius per kilometer and 1.98 degrees Celsius per thousand feet. So troposphere gets up to 36,000 feet, as I told you, and at this height, temperature is constant. It's a ISA thing. So now we have ISA deviation. So it's a standard set, no? Not all temperatures are in this earth are same. So we have to find the difference from ISA to get more knowledge about our atmosphere around we are flying. See, why ISA deviation matter? Positive deviation, warmer than ISA, so air density will be low, longer takeoff and reduced climb. Negative deviation, colder than ISA, higher density, better performance. So how ISA is calculated? First we will see. ISA temperature is calculated as 15 degrees ISA temperature is calculated as 15 degrees minus bracket 2 into altitude in 1000. So for example, we have given flight level 180 means 18,000 feet. So here we go, 15 minus 2 into 18,000 feet divided by 1000. So we get minus 21 degree Celsius of ISA, means it's the ISA temperature. So now we calculate deviation. Formula is ISA deviation is equal to actual temperature minus ISA temperature. Actual temperature is given in the question, you find the deviation, or deviation is given, you have to find the actual temperature, and we can find ISA as I told above. So for example, actual temperature is given as minus 15 degrees Celsius, and at flight level 180 we have already calculated minus 21 degree. So minus 15 minus minus 21 degree is plus 6 degree, means it's cold, it's hotter. So here our first chapter finish. So here is a one-page note of our first chapter. This is Earth, and the first layer is troposphere. As you can see, this is normal layer. This is lapse rate 1.98 degrees Celsius per 1000 feet, 6.5 degrees Celsius per kilometer. Unstable layer it is, and its height is 36,000 feet from the Earth's surface. Then comes the tropopause. It's an isothermal layer. Temperature ceases to fall here. It's 11 to 20 degrees. Then comes ozone layer, 20 to 25 degrees. Then comes stratosphere. Its inversion temperature increase here due to ultraviolet rays. It's a stable layer, range from 25 kilometers to 50 kilometers. Basically, we can say from tropopause to stratopause. It has nacreous cloud. Then comes mesosphere. Its range from 50 km to 85 km. It has noctilucent cloud. Temperature again decreases here. So we have two more concepts left with that. The Earth radiates the Earth rays, which comes to the Earth, is a solar radiation. We say it as a isolation. It is a short wave, and Earth radiates its heat back to the atmosphere. It gives terrestrial radiation, its long wave, and noctilucent cooling. So here is our first chapter. Everything is there. Just we don't have ISA. That is too. Just we don't have ISA. So that is ISA is equals to 15 minus 2 into altitude divided by 1000. It's a ISA temperature, and ISA deviation is equals to actual minus ISA. So here is a whole chapter in this short form only. Almost everything is covered here. Basics of our first chapter.